Okay, so we're going to go ahead and get started with our atomic structure unit here. And you'll notice at the beginning of this, it has a little review of the electromagnetic spectrum. And, again, we need to understand that electromagnetic radiation provides us evidence for the structure of an atom. And we should recognize some things here like wavelength, frequency. Those are things that we've talked about before. Wavelength is lambda, and that distance from crest to crest. And frequency is a Greek letter nu. Sometimes it's written as F in physics. Either one is really okay, but we measure that in hertz. And again, the longer the wavelength, the lower the frequency. So hopefully this top part is review. We have talked about velocity also. And specifically when we're talking about light, the speed of light is really 3. Let's just round this number here to 3 times 10 to the 8 meters per second. And all electromagnetic radiation travels at that speed. Okay. As long as it's going through the same medium or like a vacuum or something like that, it is going to be that 3 times 10 to the 8 meters per second. And so we have the whole spectrum here. You really do not have to have everything memorized here, but you do need to know that when we're looking at those long wavelengths like red light has long wavelengths, low frequency, and low energy, whereas the violet light and that end of the spectrum is going to have shorter wavelengths and therefore higher frequencies and higher energy. You guys are going to try a couple problems on your own then. So this first problem has us looking at calculating the frequency of red light with a wavelength of 6.50 times 10 to the minus, or sorry, not minus, but positive 2 nanometers. And with this, we might want to think about one thing, which is what is that conversion between nanometers and meters? So that conversion is that 10 to the negative 9 meters is equal to 1 nanometer. And so we can really take that 10 to the negative 9 and substitute it in anywhere we have that n for nano. And that will be how we can help us make that conversion pretty quickly. So instead of this being 650 nanometers, it would be 650 times 10 to the negative 9 meters. Okay, so next it gets into some history here, and throughout all of these notes you'll see that history. And so I do recommend you read through them because it will kind of start to connect some dots, I think. But really, some of the stuff we learned about with the atom did not come about until we learned more about light and in general about radiation. And so really we got to the point where we were able to determine that energy and frequency were related, and they are related by Planck's constant. You will notice that here we have a lot of significant figures. There's not quite that many on the AP equation sheet, which I'll show you here in just a second. So you'll notice here on the AP equation sheet that we have that very top section of the sheet telling us all about atomic structure, and it's telling us those two formulas that we've looked at so far. They are going to use C for the speed of light, and it is defined here along with H. H and C are constant values. It also obviously gives us Avogadro's number here and electron charge. But those are the two formulas that you're going to use. And you'll notice that it just looks slightly different on the notes here because it has this N in front. And that N is really just telling us that, as you can see above in italics, that there's a minimum amount of energy that can be gained or lost by an atom. And all energy gained or lost must be like some integer N of that minimum. Okay. And so he was already Planck was getting at this idea that, we can't just have electrons at any energy level. They have to be kind of these specific energies that are being gained or lost by the electrons as they change levels. And so really we get at this idea of a quantum of energy, or a very specific amount energy that these electrons are going to have. And so your next calculation has you looking at the energy of a photon. And the energy of a photon then, again, you're giving it in nanometers for the wavelength here. So you're going to have to kind of take your two formulas and do a little algebra to put them together, okay? The next part of this has a decent amount of theory really here, and part of this is that it's kind of giving you this connection and some additional information about light that we really need to know. And so one is, we call these little packets of light energy photons. We can talk about the photoelectric effect, and that's actually evidence for the fact that light will act as both a wave and as a particle. So the fact that when light hits a surface of metal, that the electrons can actually be hit and kicked out or ejected out of that metal tells us that light can act like a particle. Frequency though certainly is a specific thing for a wave. So that is also important. So there's some theory here, okay, and basically it comes down to the fact that in summary here, you'll notice it says energy is quantized, meaning it's in these specific amounts. It can only occur in discrete units called quanta. Okay? And electromagnetic radiation or light exhibits wave and particle properties. And this is what we call the dual nature of light, or the wave particle duality of light. Although there's a lot of information here that is, important, really for our purposes, the two things that we want to be able to do are the calculations. So we want to be able to use that C equals wavelength times frequency equation and E equals H times frequency equation in order to help us relate some things to the atom. You'll notice that there are some big white spaces in here because there were kind of chunks of material here that we do not need to cover, that were maybe covered in the past in an AP class, but we no longer need to cover that. So this all brings us to hydrogen's atomic line spectra. We talked a whole lot about this last year. Again, Bohr's model of the atom. And really it was supported by the emission spectrum, these bright lines or bands of light given off by the electron changing energy levels in an atom. The opposite of that is the absorption spectrum. So the emission spectrum and the absorption spectrum are opposites. It just depends on what the electron is doing. And overall, we just call these line spectra. And so Balmer actually figured out a mathematical relationship between these different energies and really the energy levels of the hydrogen atom where those electrons actually existed. And then Bohr took that and really put together that model of the atom, as you can see here, where we have our electrons occupying these very specific energy levels, or what he called orbits. But as they transitioned from the ground state to higher or excited energy states, then we could see as they transition back down, this light being given off from these very specific energies. So you'll notice that this equation here, it's really just the two equations that we talked about before being put together. And so, again, we can relate that energy of a photon specifically to the wavelength that we observe being given off by that electron. There is another equation here. You don't need to know how to use this, but I will point out a couple things that basically this equation says, that it summarizes. First of all, it says that n is an integer, okay? And so n is really that distance from the nucleus. So a larger n means a larger orbit radius. It's farther from the nucleus. Z is the nuclear charge of that particular atom. And so, again, as we're looking at that relationship between energy and distance, the negative sign implies that the energy of the electron bound to the nucleus is lower than if it would be if the electron were just an infinite distance away from the nucleus. where there's no interaction and the energy is zero. Okay, so we actually kind of reach this minimum energy. And again, you can see that, with the last two bullets there, delta E there is simply the subtraction of calculating energy at two different levels. So as we are going from a higher energy level or a more distant energy level from the nucleus, but down to a lower or closer energy level to the nucleus, we actually get energy being released. So two major defects in Bohr's model. One, it only works for elements with one electron. Well, gosh, there's only one. There's only one atom that has just one electron, and that's hydrogen. It works really great for that, but not all the other atoms that we have. And that one lonely electron does not orbit the nucleus in a fixed path. And so this is where, again, Bohr's model broke down and things got a little more complicated then. And so that's where Schrodinger came in, and Heisenberg. And when we talk about quantum numbers, we're not going to really focus on those here. We'll talk about electron configurations instead. Okay, but I will point out that really what happened is Schrodinger said, we can't know precisely where that electron is, and that's also what Heisenberg said. Heisenberg's uncertainty principle says that if we want to define the momentum of an electron, kind of where it's going, we have to. It says then you have to forego knowledge of the exact position at the time of measurement. So you can either know where that electron is precisely at that moment in time, or you can know where it's going, but you can't know both. And so that makes it hard. And that's why really we end up describing the probability of where we're going to find an electron. It's most likely that we'll find an electron in these certain regions. And Schrodinger really defined these regions based on waves. And so he said, okay, if I have, those electrons basically moving in kind of like a standing wave pattern here, they have to perfectly match up at these certain distances. So if I have 4 kind of crests exactly going around, that would be the n equals 4 level. I can do it at exactly 5, but 4 1/3, well, that's going to be a mismatch. That's impossible. And so that's really what we got at, is that there were these impossible areas around the nucleus for electrons to exist in. They're kind of energetically prohibited. And so, again, notice in the figure to the right that only whole numbers of standing waves can fit in these proposed orbits. And so that's really how we get to that idea of these very specific energy levels. You can see then, and we get into, there's some great calculus to help explain this, which we're not going to worry about, but kind of electron density models here to help us explain this. And so we can see, we have a real high density here in our picture, and it gets less and less as we go out. And we, if we start to think about multiple kind of shells, so to speak, of electrons, it starts to become like an onion for where those electrons will be. We'll get certain really high probabilities, and then in between the layers, we will have really very low probabilities. And so we'll talk about some of this stuff a little bit more as we continue on, and we talk about electron configurations and how do we know what we know about where those electrons are. So we're going to stop there for now. You should try, you certainly can keep looking at the rest of the notes, but we'll come back to those. And so we'll try to, you should try the 2 practice problems, and then we'll come back and check next week. Have a good break.